Okay, so here we are. Last time we were talking about this example here for our first example of turning a non-rectangular triple integral into a triple iterated integral. Okay, so the big idea, of course, is this sort of three-step process that we talked about last time. You go through that once for each variable, and then you repeat. Right? And you keep going until you've done all three of the variables. It's just like with double integrals where you only have two variables to go through. Same basic idea. So we walked through that for this one. And again, arbitrarily we're starting slicing in the x direction. This is what an x slice looks like. Here's the first one where it kind of just leaps out at you that's where x is equal to 0. Here's the last one, where it kind of pretty much leaps out at you that's where x equals 1. Okay, with those bounds noted, we then fix a value of x, namely we fix this x cross-section. We focus all of our attention on that one x cross-section. I emphasize one at a time, right? It's not that this is all we're looking at. We will eventually get to this slice and this slice, right? Eventually, but we're taking them one at a time, and at a time, here's the only slice. So we focus on that one slice, and then we ask the next question, which is what's the range of values of our next variable? And again, going from the outside in, our next variable is y. What is, on this x slice, what is the range of values of y? Well, y slices perpendicular to the y-axis end up just being these little line segments like that. And okay, well, where's the first one? Where's the last one? First one's over here. Pretty clear from the picture that that's in the xz plane, so our lower bound for y is 0. Last one is at this point right here, and it's not pretty clear what's going on at that point. So here's where we're going to slow down and pause and try to decide what is going on at that point. Now, is everybody with me so far? Okay. So what is going on at that point? What can I say about that point? As usual, we want to identify that point as being on certain geometric objects, surfaces in this case. And then those surfaces we will identify as having certain equations, and then within those equations we will solve for, don't lose track of what you're interested in, we will solve for y. Okay, so proceeding, here is the first thing that I know it's on. It's on this plane right there. I can see that plane. That's the plane z equals 0. I can also see here from the picture that the point I'm interested in is on this plane. That's that right there. All taken from the statement of the question, of course. And all interpreting from the picture. Notice how the picture tells us. Well, without a picture, it's really not clear which of these 4 different surfaces that define the tetrahedron are actually relevant for the point that we need, right? The picture is what does it for us. So you've got to have a picture. I cannot emphasize enough how many times I see students who want to interpret bounds on iterated integrals based on only looking at what they see in the statement of the question. And not only will that not always give you right answers, even if it does, it's not a reasonable argument, right? It's there's a certain amount of guesswork or getting lucky that you didn't realize or something along those lines. It's not a actual argument. And remember, in this course, it's not about answers, it's about arguments. So you've got to give me the argument. And so you really, almost unavoidably, have to give a reasonable picture. Does everybody understand that point? I know it's an aside, and I know I say it all the time, but again, it's really a big deal, part of the course. Okay. Alrighty. So what can I say about this point then? I've got these 2 equations. It's on the yellow plane, it's on the orange plane, and the hidden, easy to forget, third piece of information is x is already fixed. X is settled. I know what x is, and so I'm going to say it's on that plane and I just write this as x equals x. I know that looks silly, but that's just a visual reminder to me that x is known, x is a constant, or said differently, my answer may be in terms of X. Okay, so I'm interested in this green point. Want to understand that green point. That green point is on 3 geometric objects for which I have equations. The whole reason in the first place that I'm interested in that green point is that I want to solve for y. I'm looking for a y bound. So I need to solve for y. So within this algebra, where's the y? And I got to solve for it. And of course, it's right there. There's y. You solve for y. And you get that. So that then is our upper bound. Does everybody see the process? Questions? Feel free. Okay, so, all right, moving along. So we've set a value of x, thus confining us to our x slice. Now we're going to set a value of y, thus confining us in our further discussion of this example to a y slice of the x slice. And now remember, that's this right here. That's our general, generic y slice of our x slice. And with that noted, we have to proceed to finding the range of values of z. Okay, so here we go. Here's our first z slice, pretty clearly in the plane where z equals 0. No problem. Lower bound z equals 0. Where's our last slice for z? Where does z end? It ends at that point right there. And again, now we have to figure out what do we know about that point. And well, we know a few things about it. On the one hand, starting off with the obvious, x got set a long time ago. So it remains that I still know x. And of course y, whoops, I had circled the wrong one, sorry. X is known. Y just got set a couple minutes ago. So we know x and we know y. My answer may be, it's allowed to be in terms of either or both x and y. Okay, what else do I know about that point? And the last remaining thing I know about that point is that it's on this plane. Thank you, picture. Again, I emphasize, very important to have a picture. Not just for your use, but also for as a critical part of the explanation of your reasoning. The picture is what tells us that that is the plane, and therefore this is the equation that completes what I know about this purple point here. Okay. So, reminding myself that I'm looking for a z bound. I am therefore solving for z. Here it is. Solve for that z, and boom, there it is. And so this upper bound for z is that expression right there. How we doing? Does everybody follow the process? Again, I emphasize the point here is not the answer that I got to, or maybe you could have, maybe you think of it in a different way. I want to make sure everyone understands this line of reasoning for correctly and reasonably concluding these bounds. Everybody's happy with the reasoning. Alrighty, so we've got then just a bunch more examples to go through. A couple of comments before we get into them. We do have 3 differentials. Those 3 differentials can be ordered in whatever order you want to order them. You got 6 options, right? 6 different ways to arrange 3 things. And so the good news is you get to choose. The bad news is you have to choose. So choose wisely, right? Think about how to avoid bad news, just like with double integrals. Try not to slice through corners. Right? Slicing through corners is bad. It's going to make you break up your integral into multiple pieces. You could have not just 2, you might have several different integrals come up that, if you break this rule. And that nobody wants that. And again, also keep in mind what's a function of what. And anything that is actually a function of the other variables, try to put that one on the inside because you're going to have to solve for it. And good news if you can conveniently solve for it. Okay. This last little bit of advice I'm going to momentarily skip and come back to after we see it show up in the next example. So this is going to play very heavily into the next example, but I want to see the example first, then we'll come back and talk about what all that's saying. Okay. So here we go. We're going to look at the region in the first octant. So first octant means we're going to look where x, y, and z are all positive. It's in the first octant, and it's bounded by these two curves, the plane z equals 1, part of which is that, and the surface z equals x squared plus y squared, which y'all remember is a paraboloid, and all together the paraboloid is something like this, but we're only looking again at the part that's in the first octant, and so just this side of the yz plane, that side of the xz plane, above the xy plane, etc. Okay, so in our picture, this is a hard picture to draw. By the way, this picture took me forever to draw. I think it's also a really nice example of how to draw good geometric pictures. And again, I know I give you all the sales pitch all the time, but I think it'd be a really, if you're not comfortable with drawing a picture like this, and I wouldn't be at all surprised, it's a very hard picture to draw, right? Take a look at the video that I have on my YouTube channel. 2 videos, actually. This is one of the examples, one of several examples that I go through in gory, painstaking detail what aspects of what I have drawn on here help it actually kind of pop as, that's a pretty good picture. I see what's going on there. I see the 3-dimensional image that was intended. Why does that work? How is this good, and how did I accomplish actually drawing it? And what was running through my head, and therefore what can you run through your head to help you draw a picture, of this, complexity. So anyway, it's on my YouTube channel, miscellaneous topics playlists, at your leisure if you're so inclined, but I think it'd be really helpful. Okay, sales pitch over. Okay, so here's our region. And let's start going through reasoning on how should I slice this up. We notice pretty quickly z is something that pretty naturally gets seen as a function, at least in part of what defines this question. It is naturally a function of x and y. And, look, I could solve for x. Absolutely. I could. I don't want to. If I solve for x in here, I'm going to have square roots in my inside bounds, which are going to muck up my outside integrands, which is going to make my life hard, if not intractable. So I'd really like to not have to solve for x and y any more than I have to, but I'm very happy to solve for z because there it is. It's already solved for. Easy, no problem. So this is motivation to put dz on the inside. How are we doing? Does everybody follow that point? It's a really good insight to help, make good decisions on, how to turn hard problems into easy problems. Okay, so the next thing I claim, and we're going to talk through the details now, I claim that there is what I would like to call a good projection into the xy plane. First of all, let's talk about what I mean by a projection into the xy plane. That just means I'm going to take my solid, right, this whole thing here, projection down into the xy plane means I'm going to just look, push everything straight down into the xy plane. Okay, so that projection in the xy plane then is this disk. Is everybody with me on what I mean by a projection? Okay, now is where the subtlety comes in. What do I mean when I claim that this is a good projection? And there is such a thing as much better and much not better projection. So first of all, the shape itself is a reasonably nice shape. I don't hate that shape. It's not a hexagon with 6 non-parallel sides, right? It's not all that bad. I mean, okay, I'm kind of neutral on the fact that there's a circular edge there. Okay, whatever. Could be worse though. Okay. So notice that that's the first point here. The projection itself, which you might think of as the shadow, is a reasonably desirable shape. Okay. Here's the next thing that I'm going to notice about this. If you look at this shadow, if you pick an arbitrary point in that shadow and ask, okay, looking above that arbitrary point, here's this little blue line segment up there. That's the entire piece of the domain that sits directly above that point. Where is the top, and what surface will that top point always lie on? Well, the top of my line segment is that point, and check it out, it's always on this one same surface that has a single equation that defines that surface everywhere, and that's good. That's convenient. So that what you might call the top surface, easy. Secondly, the bottom point of this line segment. Notice that bottom point, no matter where the blue point is, no matter where I am in the shadow, that bottom point is always on this one surface that has the same equation across that entire bottom surface, and also, therefore, good, easy, happy. All right, so this is what I mean by good top and bottom surfaces. It's always the same equation for each one of them, and they're not bad equations. Okay. All right. So, claim then, with both of these conditions satisfied, what makes this a good projection is the fact that I can find the bounds on my original solid by just looking at the shadow. It's a kind of a surprising fact, but not that bad to observe once you see it. Let me walk you through it. So again, we've got this whole solid up here. This great big three-dimensional solid, and then I've got its shadow down here, and now let's start slicing them up. Here we go. What does a Y slice look like? Well, a Y slice, perpendicular to the Y-axis, the Y slice of the solid is something like that. Kind of hard to draw, frankly. Right? It's a weird angled slice of a weird solid that was itself hard to draw. It's annoying. What's the corresponding slice of the shadow? Well, it's right there. It's a line segment. That was easy. Much more desirable. Where are the first and last? Well, the first slice is over there for the solid, and it's over here for the projection. Where's the last slice? Well, it's over here for the solid, it's over here for the projection. And notice, of course these have the same y coordinates. This has the same y coordinate as that because it's literally dropping straight down, in which y doesn't change. So of course it has the same y coordinate. And likewise, of course, this has the same y coordinate as that. It's straight down from it. So I don't need to worry about what's the value of y there and what's the value of y there. I can instead ask the much easier question, what's the value of y there and what's the value of y there? It's just easier to do business on the shadow. Is everybody with me? Questions? Feel free. Everybody's good? All right, let's slice it up further. Looking now at a particular y slice. So again, let's focus our attention on here's the y slice of the solid. Here's the y slice of the shadow. Let's talk now about x slices of these y slices. Well, the first x slice is over here on the solid. It's over here on the projection. The last slice is here on the solid. It's here on the projection. Again, exact same x coordinates, so we're going to have the same x bounds because they're literally right up above and below each other. So the beautiful upshot here is that even though I do have to have a picture, right, I can spend most of my time analyzing all of this by instead just looking at this. two-dimensional. Much less like, corners and stuff. Just easier. Okay. Sounds like everybody buys it. So let's actually do that. And right. By the way, the one detail that I've left out. When you have a good projection in one of those directions, in one direction or another, whichever plane you are projecting into, you want to put those two variables on the outside in the order of your differentials. So the projected variables on the outside. And so notice that sort of reinforces what we'd already decided. Putting x and y on the outside per the projection is compatible with having z on the inside because of it being a function of the other. So the stars have aligned here, and both of our motivations point in the exact same order for the differentials, and so it's nice that this worked out this way. And by the way, that's not rare. I say the stars aligned very often. I hesitate to say usually, but very often this will work out this way. Okay, so now let's start slicing it up then. And keep in mind, I don't even really have to look at the solid. I can just look at my projection down here to find my x and y bounds. Because, of course, as previously discussed, the projection contains all of the information about x and y bounds of the original solid. So on this thing, it's basically a double integral question. And I can see pretty directly that y goes from 0 to 1. And then for any given value of y, x starts at 0 and ends at this point about which I know this, let's see here, about which I know this information, which allows me to solve for x2. It's basically a double integral argument, so I'm going to leave those details for y'all. And it gives us this upper bound for x. How we doing? Is everybody happy with that? Much easier than trying to slice up the solid, and worse, trying to draw our slicing up of the solid. All right. So, nice trick. I hope y'all will use that. It's a lovely point of view. You're going to see this in our remaining examples. And then the last bit, with x and y fixed, we now have to look at that x and y slice of slice, and then ask where does z start, and later where does z end. But starting off with where does z start? Well, z starts at this point, which is on this curve, which has this equation, in which I then need to solve for z, which is already solved for, and so bam. Right, so you see now why it's important that the lower surface, the bottom surface, always have the same equation. It's so that I can have a consistent expression for the lower bound. Otherwise, I got to break it up into pieces, and that's annoying. Okay, and then likewise, the upper bound is that point. So its bound, well, it's on this surface up here. That surface has this equation, solve for z, and boom, upper bound. Okay, does everybody see how that one works? All right. Okay, so the big moral on this example is to use the projection, and we're going to find that that actually helps us with lots of these kinds of questions. Let's look at this next one next. This is a surprisingly hard one to draw. You'd think a ball would be easy to draw, right? The problem is when you try to start drawing slices on that ball and then have it not look, lopsided and cattywampus. You'd be surprised. Anyway, give it a shot. I think you'll notice it's hard. So look, so you can play the game and slice, and then slice the slice, etc. And that will lead you to this answer. And one could even make the case that that's a healthy exercise and a good little bit of mathematical weightlifting. And go ahead, I encourage you to try that. But look how much easier it is if you think in terms of projections. Let's look at the projection. Now we have a lot of symmetries here, so it really doesn't matter. But arbitrarily, I'm going to do a projection into the XZ plane. Okay, art challenge time. The projection to the XZ plane is something kind of like that. I don't think I'm going to beat that for art. So, that disk, unit disk in the XZ plane. That's what you get when you take this ball and smush it into the XZ plane, right? Everybody good with that? It's unit disk. X squared plus z squared equals 1. Pretty easy to deal with from a double integrals point of view. These are the bounds. Double integral argument. We're 2/3 of the way done, and we barely got started. It's very handy, right? Much better than trying to draw the slices and see what the slices of the slices look like. Again, harder than it looks. And then all we have to do at that point is just think about, okay, if I have a point in the... I tell you what I'm going to do. I'm going to shade this in. I can reasonably. Okay, so there's our slice. Our projection. That's our XZ projection. Now I'm going to think about a point in that XZ projection, and I need to know now what's the range of values of Y on that XZ projection. And well, let's see here. It is going to have some first point back there and some last point over here. And what do I know about these points, and what do I solve for, etc.? Well, these points are actually pretty easy to understand. The key thing to know about that point is it's on the unit sphere. Right? Again, geometric appeal. Got to have a picture. The picture tells me that when I'm moving left, right from that purple point, the last one inside the ball is when I'm actually on that sphere surface. What am I solving for? I'm interested in finding a Y bound, and so I'm going to solve for Y in this equation, and I get these two answers right here. Is everybody with me? Okay. So much easier to make a projection argument. Here's a tough one. There is a trick to this one that makes this otherwise very difficult problem much more reasonable. This is a trick that I've actually inadvertently foreshadowed at the start of the course. You may recall that I made an observation, seemingly randomly, that if you have an equation that doesn't have any y's on it, that resulting surface is parallel to the y-axis. We made the argument about planes, but it's actually true about any surface. No y's means that the surface is parallel to the y-axis. And conveniently, I noticed that we actually have 3 of those in this list, right? So the question gives us 5 planes, and you could imagine the nightmare of trying to take 5 randomly angled planes and figure out how do they intersect in which ways, and what is my resulting solid, and how do I draw that? It'd be a nightmare. In general, if I gave you 5 random planes, it'd be unfair question, right? But the fact that these 3 equations have no y's means these 3 equations parallel to the y-axis makes these actually pretty easy to draw. Parallel to the y-axis just means I'm drawing stuff that points that way, and I can understand what these look like pretty directly. Actually, let me color code a little better. Z equals 0. Boop. And of course, now as a plane, I know it's parallel to the y-axis, and so it's kind of like this as a plane. Let's look at this one, z equals x. Nothing to it. Oh wait, it's a plane. It's parallel to the y-axis, so again, it's something kind of like this. And then lastly, this x plus z equals 2. No problem. Drag that parallel to the y-axis. And you can see what we've got then is this kind of prism-looking shape. That you can see right there in the picture. How are we doing? Is everybody on board? This is a massive foot in the door in drawing what this solid looks like. And so I'm done now with actually 3 of my 5 planes. Now I just have to look at the remaining 2 and see how they intersect this this prism, this Toblerone bar. And y equals 0, no problem. That's just in the xz plane. What happens if I take this vertical slice of this Toblerone bar? Well, I get a little triangular slice like that. Nothing to it. Everybody happy? And then lastly, what's the deal with this equation right here? This is the tough one. This is a slice that's coming in at kind of a weird angle. And, so, yeah, you're going to get something that's kind of like this. How did I know to draw this exactly? One thing you could do, if you like, is think about these edges one line at a time. Oops. And so, for example, on this edge here, where x is 2 and z is 0, solve for y, you find that y is equal to 1 on that edge. And then you can say, okay, well, how about on this edge up here, where x is 1 and z is 1? What happens there? Well, then that gives you different information about y, and then last edge, again, solve for y. And I don't know how good a job I did at drawing this, but anyway, the punchline is that plane's going to cross-section and something like that. Is everybody okay? All right. Okay, and now it's all over, but the details. You can proceed in either of 2 possible ways. I'll point out first that the only slicing that doesn't slice through corners is this one. And this is there's 5 different options, and I encourage you to go through and attempt to slice this solid in the other 5 orders. You will slice through corners. For example, if I were to do my Y slicing on the outside, right? These Y slices, well, here, let me cheat. My Y slices, as I slice through, I'm going to inadvertently slice through that corner right there. And then also this corner right here, which is annoying. So no good. So we're not going to put dy on the outside. Everybody buy it? And just, again, go through all your other options. They all stink except for this one. And notice, doing my Z slicing on the outside, my slices all look kind of like that. And they'll look the same all the way up. I mean, they're, slightly different, but I don't slice through any corners or edges as I go up like that. And then as I take X slices of that, my X slices all, my X slices, again, fine all the way, start to finish, no corners. Okay, so now you can take that point of view, and that's a good one, but as you know, I'm a big fan of projections. Notice you can also very easily observe, once you have a good picture, you got to have a good picture, essentially. Notice there's a really good projection into the XZ plane. The shadow is a triangle. I love triangles. Right? Where's the upper bound surface? As I move perpendicular to that shadow, as I move in the direction of the projection, my upper bound surface it's always this same plane. My lower bound surface is always, this same plane. So good upper bounds, good lower bounds, good shadow itself. We're in business. And so with that said, I put dx dz on the outside. I can look at the projection here to find the bounds for x and z. Now again, that's a double integral problem. Think through which way why dx dz, why not dz dx? It's because of how I want to slice up that projected triangle there. Right? You get these bounds like this. And then, as I move in the y direction, my first y bound comes from that point, which is on this plane, which has a certain equation, and solve for y, and I get 0, of course. Also pretty evident just straight from the picture. And then the last value of y comes from this plane, because that last point is always on this plane, which has, let's see here, come up here where I can, anyway, it has this equation in which I can solve for y, and I get that as my upper bound for y. So again, much easier from a projection point of view. How are we doing? Okay. Yep.
Is there also a way to do this like multiple points?
Yeah, I mean, yeah, you could chop it up into pieces, yeah, and make the problem 3 times as hard. Yeah, you could.
It would be like that much harder.
I mean, it depends on which way you slice. So there are 5 other options of how to slice it, and some of them are worse than others. But this is the only way that will leave you with a single iterated integral to compute. So this is, I'm going to say, a highly preferred method. And so just to extend beyond what your question was, don't forget it's not about the answer, it's about the quality of the reasoning. If you strategize poorly and end up making the problem twice as hard for yourself, that's not good reasoning, right? And so, strategizing the best way is part of the goal. It is part of what we want to see on tests and homeworks. Okay. Alrighty. Okay, moving along. Another hard one. What a weird surface, what a weird solid this is. It's what is between this paraboloid and this paraboloid. And so again, my solid is what is bounded by, there's that expression again, bounded by those 2 surfaces. And so it's this, I don't even know what to call that. Is everybody on board? Everybody see what we're talking about there? Tough picture. Now again, one thing you can do, it would work if you just started doing slices of the solid. Various bad things are going to happen as you try to slice in various different orders. And what's going to end up being a good choice is this choice right here. And again, different ways to motivate this. One motivation is I notice that I really want to think of y as being a function of x and z, because that's how the algebra comes to me. That's how the algebra looks the nicest. Let's arrange for y to be a function of x and z, and to be compatible with that, we put y on the inside of x and z. Everybody good? Okay. Also, whoops. Yeah, anyway. We have a good projection into the xz plane. Now again, I just see that from the geometry. If you project into any other plane, weird things are happening, right? This is the good direction. And I have a very well-defined lower bound surface. And I have a very well-defined upper bound surface. As I move perpendicular, from a given point in my projection, as I move perpendicular to the inside axis, moving in the y direction there. And my y bounds are going to come, lower bound from the green surface, upper bound from the blue surface. Is everybody happy? So I like the projection point of view much better on this one. Okay. All right, details, of course. But notice, again, I've got my colors forgotten. Yeah. So this surface here then gives me my lower bound for y, and this surface here gives me my upper bound for y. Okay. All right, moving along. So that does it for 5.4. We're moving now into 5.5. This is another one of this book has several of the following, what I like to call monster sections. 5.5 is huge. It is, if you were to break it up into two sections, they would still be pretty big sections. Change of variables, there's a lot to say about it. And then the second half of Section 5.5 is a particular application of change of variables called doing integrals in different coordinate systems. And it's very closely related to change of variables, so that's why they put it in this same section, but it really very well could be, arguably should be, its own section. Massive section that we're going to have to deal with. So we're not going to get through this today or Friday. So anyway, I want to segue into this by flashing back to single variable calculus. As y'all recall, I like to do this, right? I motivated the big ideas of how we think about multivariable derivatives by reminding us how do we do single variable derivatives and then sort of extending that naturally. Likewise with, where did I come up with double integrals and triple integrals? Well, we reviewed, we looked back at single variable integrals. Wait, what fundamentally is a single variable integral? And then we extended that concept. So, here's another flashback. Substitution rule. Everybody remember the substitution rule for integrals? And this, it was just written in terms of algebra. Here it is. Substitution rule for integrals basically says that if you have x equals g of t, you can, kind of plug that in and work out the integral that way, right? Now, I want to give you a geometric point of view on that. This is going to be important for extending into the multivariable context. I know y'all know single variable calculus. Again, that's not my purpose here, but I want to take this particular point of view. So our function g, x is equal to g of t, means the function goes that way. Okay. And let's suppose, by the way, that we have this integral that we want to compute. So this is what I want to be able to solve for. I've got a function that that goes toward, you might say, toward that integral, right? So how does that then get rewritten? And the first observation I want to make is an observation about something called a pullback. And it's ultimately a pretty simple observation, and that is functions will push points forward, but they pull expressions back. Let me give you an example of what I mean by this. If you have a function like this, and let's say you've got y is equal to s cubed minus s, let's just say, and so that takes me from the s-axis to the y-axis, right? So I've got a function there. If I have an expression cosine of s, how would I push that expression forward? I don't know. I would need to solve for s. I don't know how to solve for s. That's not really how plugging in works. Whereas on the other hand, much easier. If I had an expression over here, cosine of y, no sweat. This will do, again, what we call a pullback. Right? Something written in terms of the output variable can be rewritten as something in terms of the input variable, in this case s, just by literally plugging in cosine, let's see, well, y. Oh, okay, well, y is this. Just plugging that in. And boom. So this is what I was talking about. We think of functions as going a certain direction in terms of which way do they send points. And points push forward. Expressions pull back. Everybody on board? Okay. Well, an integral is an expression, and so if I have an integral on the right-hand side here, an integral on the x-axis, an integral written in terms of x, however you want to say that, the function pushes forward, the expression pulls back. Is that all right? Okay, so the next thing I want to talk about related to this is what I like to call the stretching factor. Now, again, y'all know the substitution rule, and here's our new integrand. This is the integrand that you get when you do when you plug in the substitution rule, and it's just a rule, and you can think of it that way. But here's another really good way to think about it. If I have a dt over here, I think of a little piece of width on the t-axis. When that pushes forward, you're going to get a different interval over here on the x-axis. There's no reason that we should suspect that that's going to be the same size. Right? Why would dx equal to dt? They're different variables. They're just not the same thing. And in fact, pretty easy to make the case from previous, single variable calculus that dx is g prime dt. Right? So in that process of pulling back, think of where that g prime comes from, right? It comes from that expression that tells me the relationship, but you can also think of that as that this thing here, g prime, is telling you by what factor is the output interval bigger than the input interval. Right? The output interval's bigger. It kind of got stretched out, and it got stretched out by a factor of g prime. So I'm going to call g prime the stretching factor. So a way of keeping track of the fact that output intervals are not the same size as input intervals. Is that cool? Okay. All right, and then other details. Right? Let's see. I guess while I'm here, I will point out that yes, points push forward. Also, intervals push forward. If I have bounds a and b, that represents an interval on the t-axis. When I plug in all the points of that interval into the function g, a goes to g of a, b goes to g of b. And so this interval from a to b turns into this interval, which you can see here is from g of a to g of b on the x-axis. So, said differently, when you do the pullback, right, this interval from g of a to g of b has pulled back to this interval from just a to b. So, another way to think about the setup that we have here. Okay, all of that said, I claim now with this as a model, we can try to do the exact same thing in 2 dimensions. And here's roughly what it looks like. Let's, excuse me. Suppose I have some interval over here in the UV plane, right? And then I say I've got a function that gives x and y as functions of u and v. Call it g, just like we did in single variable. And let's see here. The output then is going to be this other interval, which, multivariable functions being as weird as they are, who knows what that shape's going to be. You have some wacky, weird shape like that. With corners and curves and yikes. Okay. So, that said, if I have an integral, for whatever reason, on this nightmare output shape, if I need to compute the amount of mass on it, or the number of people living inside of it, or whatever, that output interval, right, I can pull back, I argue. Well, details need to follow. But hopefully, fingers crossed, presumably, I'll be able to pull back that integral, dx dy, into an integral over here in the UV plane on our pullback domain, which is a rectangle, or anyway, something convenient, hopefully, presumably. We're going to try to arrange it to where the pullback is nicer than the original. And the problem that I was faced with originally of computing this ugly integral on an ugly domain. Look at the corners, and imagine as you slice that up, you're going to be hitting corners no matter which way you go, right? This is a highly undesirable integral, and I can turn that instead into, we hope, an integral over here on my nice, planned, rectangular, highly desirable pullback domain, du dv. Big plan. Notice it's a shameless ripoff of what we've already done in single variable calculus, and the only thing that's actually to be figured out, and some of this is sort of obvious. What is x comma y? How do I rewrite x comma y? Well, that's the very definition of the function g. X comma y is what g of u comma v gives you. So, I mean, plugging into an integral, nothing deep happening there. The only detail to be worried about is how much bigger is this output piece of area, dA, than this input piece of area, du dv. Right? So I got to figure out what this stretching factor is. That's going to be the big question. And then it's just a matter of plug and chug and go about your business. So I see we're out of time, so we will draw the line right here. We'll pick up here on Friday. And y'all have a good rest of your Wednesday. See you later. Don't forget to make sure to let me know if you came in after I did attendance.